Hello everyone, welcome back to the channel. Today we are tackling coding problem number 14, the longest common prefix. Previously I have solved this problem using the brute force and binary search approaches. I'll link those videos in the description below, so feel free to check them out if you haven't already. I would suggest going over those videos first to get a good foundation. In this video, we will explore another powerful technique, the divide and conquer strategy. I won't be diving into the basics of what is prefix or the initial steps like asking clarifying questions and making assumptions. Those are covered in the previous videos. Instead, I'll jump straight into how to efficiently solve this problem using divide and conquer. So let's get started. The problem requires finding the longest common prefix string among an array of strings. And if no common prefix exists, the function should return empty string. Like here in this example, FL is the longest common prefix among this string, so the output is FL. And here in the second example, there is no common prefix, so empty string is being written. What is divide and conquer strategy? So divide and conquer strategy is a problem solving approach that involves breaking a problem into smaller, more manageable subproblems, solving each subproblem independently and then combining their solutions to solve the original problem. So as you can see it here. So basically this approach consists of three main steps: divide, conquer and combine. So in divide step, the problem is divided into smaller subproblems, and the conquer steps focuses on solving these subproblems, often recursively, until they become small enough to be solved directly. And the main important part is base cases. So base cases are essential in conquer step to stop the recursion and transition to the solution. And finally, in the combined step, the solutions to the subproblems are merged using a helper function to obtain the solution to the original problem. And this strategy is widely used in various algorithms to efficiently solve complex problems. So I have detailed the divide and conquer strategy thoroughly in this GitHub file, which I will also link in the description. Let's see how we can use this algorithm to solve our problem to find the longest common prefix. So the first thing is we will establish our base case. Like if the array of strings contains only one string, the longest common prefix would be that single string itself. So that would be our base case. So that was our step one, to establish base case, which is necessary for stopping the recursion in the conquer step. Okay, so moving to the next step, like that is to divide the array of string in two halves. So let us consider this as an example: flower, flow and flight. So we would initially divide it into left half and right half. So in the left half it would be flower and flow, and in the right half it will be flight. Then we further divide each half. Like for the left half, flower and flow, we divide it into flower and flow. So in the left half we now have flower, and in the right half we have flow. Then we find the longest common prefix for each half independently. So for the left half, which contains flower and it's just one string, and we saw that in our base case, if the array contains only one string, then return that string as the prefix. So for this, then the longest common prefix would be flower, and for the flow, the longest common prefix would be flow. So now the fourth step, which is combining the results. So we compare the common prefix of the left half, that is flour, with the common prefix of the right half, which is flow. So by comparison, we mean here like we compare character by character and find the longest common prefix for the left half and the right half by using some helper function. So it would give us FL as the longest common prefix, and similar thing we would do for the right half as well. So here we just have flight as one string, and since it's just one string, we will get longest common prefix as flight. Then we would compare FL with flight. By comparing character by character, we would find the longest common prefix for FL and flight as FL, and we would return this as our longest common prefix. So that's the overall idea on how divide and conquer works. So let us code that out so you will get more clarity. Let me start coding this. So here is the main function which takes the input as array of string, and here we will start with our edge case, which is if this array is empty, then we will return an empty string, and then if that's not the case, then we will just return the output from one of the private recursive function which we will be implementing for our divide and conquer strategy. So it will have basically three parameters, which is input array, then left pointer and right pointer. This is basically the entry point of our algorithm. So now let me write the private recursive function. Now let me start with the divide and conquer strategy, defining the function where the divide and conquer strategy will be applied. It would be something like private string. So let me start the base case which is needed for recursion to stop, and also one of the important steps in the conquer to get to the solution for small problems. So it would be something like if the left index L is equal to the right index R, it means there is only one string left in the current segment of the array, and in this case the function returns that string. So if L is equal to R. Now for divide strategy, which is our second step, let us divide the problem using mid as L plus R divided by 2. So else we'll calculate our mid point using L and R divided by 2. Now this will basically just divide the problem. Okay, for that we need to make two recursive calls. That would be basically our conquer strategy, like to solve the subproblems, where we will make two recursive calls. So one will be for left half and one will be for the right half. So this is basically our conquer strategy, and this is our base case which will stop these recursive calls. Okay, and after that we need to combine them using some helper function. Let me just give that helper function name, say common prefix, where we'll pass this left half and right half. So once the recursive calls return, you obtain the common prefixes for the left and right halves, and then combine them using this common prefix function. Let us go over what that helper function will be. So it will be basically private string common prefix string left and string right. So this function takes two strings left and right, representing the common prefixes found in the left and right halves of the array respectively, and it iterates through the characters of both the strings simultaneously until it finds a mismatch or reaches the end of either string. And if it finds a mismatch at any index, it would return that substring of left up to that index. And if no mismatch is found, it returns the entire left string or right string. So now let's dive into the common prefix helper function. This function is key in our divide and conquer approach, as it helps us merge the results from the two halves of our problem. So as you can see here, the common prefix function takes in two strings which represent the longest common prefix found in the left and the right halves of our array. And the goal here is to find the common prefix between these two strings. So the first step is we need to determine the shorter length between the two strings, because the common prefix cannot be longer than the shorter string. This is done using mat.min function. So I will take a variable, say min, and use mat.min function to get that minimum length. Okay, now next would be to loop through both the strings character by character. So for int I equal to 0 less than min I plus. Here we compare the characters at the same position in both the strings, which we can do by using left dot char at I. So basically, if we find a mismatch, that is if the characters are not equal at that position, we immediately know that the common prefix ends right before this position. So we will return the substring from the beginning of the string up to the mismatch index from 0 to I, as this end index is exclusive in substring. And if no mismatch is found, it means one string is a complete prefix of the other. So we return the shorter string. Okay, now we need to understand the time complexity for this one. So we will use the Master Theorem to analyze it step by step. I have already detailed that out in this GitHub file, whose link as well I will post in the description. So the first step in analyzing the time complexity is to set up the recurrence relation. That is the step 1. So since we are using divide and conquer, we split the problem in two subproblems of size n by 2 and we combine their results. So this gives us that recurrence relation. Suppose the main problem takes t of n time, then the subproblems would take t of n by 2, and we have two subproblems, like the left half and the right half. So 2 t n by 2 plus O of m. So basically O of m represents the time complexity for comparing two strings to find their common prefix. So yeah, so what that means is m is the length of the strings being compared. When you compare two strings character by character to find the longest common prefix, in the worst case you might need to compare up to m characters, where m is the length of the shortest string. The next step would be like we need to compare with the general form. So actually I have given that master theorem for dividing function in the GitHub, like all the details, like what we need to do step by step. Like we need to first calculate the two key values and different cases. So when we compare our recurrence relation with the general form, we get here like a is 2 and b is also 2 and f of n is O of n. So here we will compare our f of n function with the standard form, which is this, and use this to calculate k and p value, something like this. So here we can see k is 0 and p is also 0. We will compare our log a to the base b and k value and check which case fits. So basically now there are three cases which we need to see where our key values fit in. Log base b of a, if it is greater than k, then this is how we will calculate our time complexity. Here we can see log base b of a is actually greater than k. So our we fall into case 1 of the master theorem, and case 1 tells us that the time complexity is dominated by t of n by b part of the recurrence. They have not considered f of n. It's mainly dominated by t of n by b part of the recurrence. But in our case, like we will have this O of n for sure, but we also need to account for the complexity of combining the results, which adds an additional O of m factor. Therefore, the overall time complexity becomes O of n into m. If you want to read more about it, like why we have considered O of m, so I have detailed that out here as well. Here is the main part, like the total work at each level is not just constant. So at each level there is like O of m work being done, and that's how like O of m also becomes part of the overall time complexity. So the recursive part of the relation simplifies to O of n, as you have seen in our master theorem here, and this basically represents the number of levels in the recursion tree. And the merge step, that is where the helper function is being used. So at each level we will use that, right? So each level of recursion involves a merge step that takes O of m time, and that's how like we have considered our O of m in overall time complexity. So now let us talk about the space complexity of our divide and conquer approach for finding the longest common prefix. So whenever we use recursion, there is some memory overhead because each recursive call needs to be stored in the execution stack. So this memory is required to keep track of the function calls, parameters, and return values. And in our approach, we split the problem in two halves at each step, right? So this results in log n recursive calls, where n is the number of strings. And the reason for this is that with each division, the problem size reduces by half, and this continues until we reach the bits case. And for each of these recursive calls, we need space to store the result. Since we are dealing with strings, and in the worst case each string could be of length m, the space required per recursive call is m. Now since there are log n recursive calls and each requires m space, the total space complexity is O of m into log n.